these things about with reference to Mangalyaan or what is relevance of that, because whenever you send something at other planet, you need to communicate with it, and then you need to take pictures of that, and actually majority of the things is taking pictures and analyzing that. So we need remote sensing technology for that. Now remote sensing technology is actually using the full electromagnetic spectrum. If you see right side, like this is actually picture of see, if you take different frequency bands and take a picture of Earth or any other planets, how it will look like, and same thing about the nebula, Crab nebula, it is there. So if you take a radio frequency, if you take at infrared frequency, then visible band, everywhere it is like this. Now we have actually two types of remote sensing satellites available with us. One is optical and IR, another is in microwave band. In microwave band we cannot get good resolution. For that there is a special technique called synthetic aperture radar. So that is one way you take a good get a good resolution. Resolution means you have different types of resolution. See, suppose you are taking a picture of certain place, so you need a spatial resolution, that is in space how much you can resolve it. That is, a chair should look like a chair, it should not look like a dot. So that is one. Another is called spectral resolution. At different spectrum, frequency spectrum, how it gives the signature. Another is temporal resolution. Temporal is how frequently you can take the picture. Another is called radiometric resolution. Radiometric means, okay, basically you can think it as a contrast, how good the picture quality is. So these all things you normally see at that. And now optical remote sensing, you see we started with around 300 meter, 1 kilometer of resolution in spatial resolution. That is 1 kilometer we will be looking like a dot. But today we are at 0.25 meter, that is 25 centimeter. 25 centimeter resolution you can take a picture from space, and this is a city looks like. So it normally you see in Google Maps all these things, but the problem is if you see in Google Maps you will see a picture probably of 6-month old. Now here you get live pictures depending on the temporal resolution. So that's the advantage. And what are the things necessary for that? One is the telescope. Telescope is the main part of your optical remote sensing payload, and synthetic aperture radar is another technology where it is microwave and antenna. These are the two technologies, and whatever be the technologies, finally you take the picture, you are taken the light from the lenses. Now you need a detection. Now detection, like it's very easy if you see your mobile, and when you see it, okay, it is in optical frequency, you get the detector plenty available. But when you talk about infrared or below infrared, far infrared or X-ray or gamma rays, there is nothing available in the market what you can purchase and use, make your camera. So those all detectors are to be made. So this is one great challenge, and you see lot of detectors what ISRO has designed. I have put few of them here. Now this is you know about radars. What radars do? They take the same things, same pictures, but take it in a different way. So these are the frequency band, L band, S band, X band. They are actually identified for radar frequency band, and we have L band radar, S band radar, and X band radar. So these are giving different signatures of a picture whatever you take of different places. Particularly in this region, I remember we have a project with IIT Kharagpur, like mining region. In mining region, how the crops, how the plants will be behaving, how will be the plant health, because the mining deposits, the dust and other deposits are getting on the leaves of the plants. So how they will be affected, how their health will be affected by that. We have different projects for that. And these are used in planetary missions also. Chandrayaan used this synthetic aperture radar at L band and S band, and right now we have projects of covering Earth. that is taking picture of Earth on L and S band, and that is called L and S bands are, that is NASA ISRO joint collaboration is there, and now the satellite is getting integrated at our URSC, that is Bangalore Center. This payload was also done at SAC, at Space Application Center where I work. And okay, these are the different subsystems. If you see, they are actually this is called MINISAR, mini synthetic aperture radar. Here you have lot of components which are using actually advanced semiconductor devices, not only silicon. Now probably you will be listening about gallium nitride. If you see your mobile charger is nowadays actually using a different technology, gallium nitride, which is much more efficient in terms of power. So here we made all these devices ourselves, then we packaged them, and then we have flown it on, this was flown on aircraft to image the Earth. Okay, now this is, I told you about the taking pictures, then next is the communication. Next, if you are sending something to even around the Earth or other planets, there will be, when you are taking pictures, you can see that whenever you are taking pictures in your mobiles, you tell my mobile memory is filled. Now if the memory is getting so fast, filled so fast, now what will happen to the pictures of Mars or lunar orbiter? They are taking continuous pictures and trying to send on Earth. So you need a very high bandwidth link between Mars and Earth, or say Moon and Earth. So these are the technologies. Actually we made these chips. With these we make data transmitter. These data transmitters are sitting on the satellite, and they are beaming on Earth to all these satellite, all this data, what it has captured. Now these I have told you 3 components. Now this is another one, is 4th type of technology what we need to make. That is, suppose you have sent a satellite. Now one face is looking towards sun, another face is looking towards, say, the cold sky, and sun and the face which is looking at cold sky, that is temperature is of that place is around 4K or in that range, and which is looking at sun, that is getting very hot, and your payload is going to see all those temperature. Now no electronics will work on that. So what you can do about that? So minus 269 degrees centigrade to say 150 degrees centigrade, it's impossible. So there are different ways for thermal management. That is one place when it is heated, so you take thermal, they call it heat pipe. You carry the heat by pipe on the place what is getting cold. So that way the whole thermal management of the satellite is done, and the payloads which are going to work, that is always maintained at minus 10 to plus 60 degree within that temperature. So your electronics is safe. So but lot of work is to be done by for that. And when you go up, your air pressure decreases. So the problem is that now whatever you tested on Earth, that was in certain temperature, that was on certain pressure. Now what happens? Suppose you make a filter, say what is called a microwave filter. Now it's a waveguide cavity. Now waveguide cavity you tested on Earth where the air is there. Now when you go there, the no air is there. So what happened? What do you call it? Dilating, that changes. Now its frequency shifts. So it doesn't work. So you have to test all of them in vacuum as well as in temperature. So this is the so we have to simulate the space environment. So this is the system which simulates the space environment, that is normally called thermal vacuum. That is, you make vacuum and then inside that you increase. Now whenever you make test on thermal, what do you do? In space there is only radiation. You don't have convection or conduction. Conduction you can do some way, but convection is not there. So that way you have to, we use liquid nitrogen to cool that. So cooling that, we do the testing by cooling by liquid nitrogen and heating by IR lamp. So these are the ways these chambers are made, and then there is high vacuum inside, and then you push your complete satellite inside and take the electrical signal out of it, and from there you see that how the performance of that electronics or mechanical system, how it is there over the space environment. That is called space environment simulation test. So this is the way to test it. So after so much testing with so many components starting from your devices, that is chips, to the final subsystem, you get a satellite. And this is the exploded view of our Mangalyaan. So after having that much background only, now you are qualified to make a satellite which is going out of Earth and going to circle around Mars and going to send you pictures. Now if you look at this satellite, this is having different part. One is solar cell, definitely you can see as long solar cell. Then you have different payloads. Payloads is which are going to stay there and take pictures. One is Mars Color Camera, MCC, you are seeing here. Then methane sensors. Then thermal infrared imaging system. Another is MENCA payload, they named it. That is actually exosphere, that is Mars outside. What are the elements there? It will give a signature of those elements. So these all these are the experiments you are going to carry out while you are on Mars. And the right side picture, whatever you are seeing, that is this satellite integrated with our PSLV end stage. Okay, these are the better view of your different subsystems. First is Mars Color Camera, next is thermal infrared imaging spectrometer, then methane sensor for Mars, and then Lyman alpha photometer, and Mars exospheric neutral composition analyzer. Now what these all gave you? So after, see, this payload was designed to work only for 6 months. But it is still today it is working. So 7 years after a completion of 8 years, last year September, there was a conference for update in Mars orbiter mission, and national meet they organized. Now what actually it made out? The original intention of it, okay, we are going to demonstrate the technology that okay, we can reach Mars. And next was the science. Actually, science was the secondary goal here, by the way, because we are not sure that whether we will have the technology to go there, and so everybody was skeptical about that. But still, we thought, okay, we will send some payload which will be actually useful for different work. Now, I will tell you what all things we have done. Now, Martian exosphere, that is outside the Martian environment, whatever elements were there, it has analyzed. And what it has done actually, Mars is normally a thin atmosphere with CO2 only. So after reaching certain height, and when the day is, dusk is there, that is day is changing to evening, that time what it has found that okay, its carbon dioxide environment actually changing to oxygen environment. That was an important finding, that okay, though the environment is thin, but still it is having sufficient oxygen level. And then Mars is probably, if you have seen the Martian movie, you have seen a dust storm. So, and what actually separated them. And it has taken few good pictures of dust storm, how it is occurring, and genesis of that. So that was also another important observation of Mars atmosphere. And definitely it has taken good pictures of Mars, whatever is having craters and volcanoes and all of them. And then there are certain ranges I will show you, that it looks like that it was an ancient rivers. That is, suppose on Earth, if you see that one river bed is there, but there is no water today, and if you take the photograph of that range and how it looks like, almost similar is there in Mars. So that also gives some clue, probably someday the liquid water was available there. And then how hot or cold is the planet, and what it is radiating. These all instrument has captured all of them. And for now you have the data captured, you have the data transmitter system sitting on Mars orbiter mission. Now we have to take the signals, you have to accept the signal on Earth, and this is the elaborate arrangement what is there in Bailalu near Bangalore to get the data reception system for these science missions. That is, this is a 32-meter big antenna what it is accepting the data which is sent by the satellite in X and S band. And if you see the right side, there is the earth station system. What are the components? See, if you see, there is an antenna, you have a low noise amplifier, then you have a down converter, and you have the data demodulators and all of them. And with that, you have recovered the data, whatever was captured there, and with now those data you will simulate it now, how it works. And about the latency, I have already talked to you. Now this was the picture what I was telling that, okay, it was taken by MOM, and this is the full disk image. Now full disk image is because it is a elliptic orbit and it has taken from the far distance, so then you get a full disk image. And in left side, whatever you are seeing, basically it is taken in different color. If you take with different color filters, it gives you different impression. See, red color is, if you are taking red color picture on the camera, there is, you have a red filter. What it takes is that, okay, what you see is that maximum radiation of the planet is red. So that is the maximum brightness. So that's why from Earth, if you look at Mars, you always see it is called a red planet. Now, if you take a picture with blue filter, what actually it gives is that how is the dust coverage on that, how environment is covered by dust and other things. And green also, it gives a different view. And when you take the full color, it looks like this, like your full disk image. And okay, another is geological feature, that is it